So this is the lab lecture video for the theory, background, and calculations for the determination of the equilibrium constant lab. This lab is using the same theory as the spectrophotometric determination of iron lab. We're still using the spectrophotometers to measure absorbance, and we will be using Beer's law. And part A of this lab, its entire purpose is to calculate to determine the extinction coefficient to be used in Beer's law to use in part B. So for this lab, the balanced chemical equation that we're doing is involving iron, but this time it's iron 3 ion instead of iron 2 ion, which, I mean, obviously they're different or else they wouldn't have a number, but they're even visibly different. Iron 3 has a yellow color, where the iron 2 was colorless. It only changed colors once it did its reaction. Well, we'll start with, this is a reaction that goes to equilibrium. Okay, so color-wise, iron 3 is a yellow color. Thiocyanate, SCN minus, it's a polyatomic ion. It's just not one that you've seen much of. Is colorless. And then the product is supposed to be what a lot of books describe as blood red, which I just think it's fun to call it that. But usually in the lab, for whatever reason, it comes out kind of an orangey red color instead of this amazing blood red color that I want. So this is the reaction that we're doing. And the end goal, like the final goal for this reaction is to calculate the equilibrium constant. And it's going to be, Kc. Okay. So, just like with our equilibrium stuff in lecture, products over reactants, we're doing Kc, so molarities. So Fe NCS2 plus over iron 3 times SCN minus. All of them have a coefficient of 1 in front of them, so they're all raised to the first power. All three of them are aqueous, so they're all part of the expression. So to solve for Kc, we're going to need to know the equilibrium concentrations of all three chemicals. Again, we're going to be using spectrophotometric analysis to determine, that's the method, the procedure that we're following for this. So before we can get to this equilibrium reaction, just like with the last lab, we have to do part A, which part A's purpose is to find the extinction coefficient. Which is that value that we need for Beer's law. Okay, so what we need to do is do this reaction, but do it in a way that we can accurately know the concentrations. We need to make standards. So the added extra fun bonus for this lab is the reaction that we did with the spectrophotometric determination of iron with the last one. It was not a reaction that goes to equilibrium, or at least not significantly. It pretty much goes to products. Okay. So we made sure iron was the limiting reactant, and it was a 1-to-1 mole ratio, so we were able to calculate the concentration of the product to know the accurate M1, or to solve for M2, anyway. Oh, and I didn't mention, but this is the chemical that's being tested by the instrument. Okay, so that's the chemical that the instrument's going to measure. So the issue with this one is that this reaction goes to equilibrium, which means I don't really accurately know any of their concentrations without an ice table, and that's the opposite of helpful when I need to know their concentrations. Now, we are going to be working with molarity for this lab. So what we have to do is we need to find a way to take this same reaction. I'm just going to rewrite the balanced equation, but make the arrow just left to right only. Oh, and the FeNCS2 plus, I know it's in a different order, SCN, it's like backwards. Just that's how the iron attaches, is it attaches to the nitrogen, so that's how it's written. But we need to make this reaction be a left to right arrow only. So what we're going to do, and this is the official scientific term, is add a crap ton of iron to make the reaction shift, following Le Chatelier's principle, right. So where it only shifts to the right. So we are going to add in part A a different molarity of iron, 3 ion, than we will in part B. Okay, so we're going to be adding a 0.2 molarity iron solution, a 2.00 times 10 to the negative third molarity SCN minus solution. So we're setting this up so the thiocyanate, the SCN minus, is the limiting reactant, and we're going to say this goes to completion, this goes to products. Okay, so what we need to solve for are going to be the concentrations of the product for each of our standards. Okay, well, if this reaction truly does go just left to right, then we really can use M1V1 equals M2V2. So if we look at the data table for part A, the first row is the volume of the sodium thiocyanate. So just like previous labs, I cannot get a beaker of SCN minus. We need to have a cation, a positive charge, to cancel that out. So sodium is the spectator ion. Sodium's not part of this reaction. That's why it's listed in the everything, but it's not listed in the equation because it was canceled out as a spectator ion. So first you're going to record the volume of the sodium thiocyanate, which it comes straight from the table in the procedure on how many milliliters of that you're going to pipette into your 50 milliliter volumetric flask. And then it asks for the thiocyanate SCN minus molarity. Well, you can use M1V1 equals M2V2. We know the molarity of the stock thiocyanate. You know the volume of the NaSCN, the amount that you're going to be adding using a pipette into the flask. And we're solving for M2, and we know that V2 is how much of the solution that we made, which is 50.0 milliliters. So the SCN minus molarity, you're just using the M1V1 equals M2V2 and solving for M2. It will be different for each of the solutions, so if you're getting the same number, you're doing it wrong. Right below that is the FeNCS2 plus number. Once this is now solved for the molarity of this chemical. Well, luckily for us, this is a 1-to-1 mole ratio. So whatever the molarity of thiocyanate is the same as the molarity of the product. So you're just literally rewriting the number right above it into the FeNCS2 plus. You're going to write the SCN minus number. So in part A, SCN minus equals FeNCS2 plus. The absorbance value is going to come from the instrument. And then again, the purpose of part A is to solve for the extinction coefficient, which is the slope of the graph, where we're going to put the concentration of the product, because that's what the instrument actually measures, on the x-axis in molarity, the absorbance on the y-axis. Excel is going to give us a beautiful straight line, and the slope is the extinction coefficient. Okay, and then we'll be using that extinction coefficient in part B. Okay, so that should get us through part A. You have to make this one graph on Excel, and that's part of the lab report, so make sure that you're setting that up. And yeah, okay, so let's move on to part B. So I'm going to rewrite the equation, but this time I'm going to leave it in its equilibrium format because in part B, we are going to add much lower concentrations of iron. So we're going to add same concentration of iron as thiocyanate, so that way this reaction can truly go to equilibrium. We want this reaction to go to equilibrium. Okay, so you're going to be, pipetting into the little tiny adorable volumetric flasks, and at some point taking a temperature. Since we're doing equilibrium constant, we have to know the temperature. I'm just going to record this again. We did this in the last slide, but the equilibrium constant expression, again, our goal is to eventually get there. Okay, so on the data table, first row is the volume of the iron 3 nitrate, which you're getting from the procedure. Second row is the volume of the sodium thiocyanate, which you're getting from the procedure. And then the calculations begin. The initial iron, now I know all of a sudden the nitrates are gone. Again, the nitrate is a spectator ion. It's not important. So when we're solving for the Fe3 plus initial, we're just doing another dilution equation. You were told M1, I think it's 2.00 times 10 to the third molarity. You were told V1, that's the volume that you pipetted. V2 is the total volume, which is 10.00 milliliters. So you're just solving for M2. Then you're going to repeat that procedure for thiocyanate, just using the thiocyanate numbers. So the M1 for thiocyanate just happens to also be the same value. The V1, the volume of thiocyanate, make sure you're looking at the correct volume when you do this. It's not going to be the same volume as the iron. V2 will be the same though because you mixed these solutions together to get a total volume of 10. So you can do those calculations before you've even done anything else. You could do it before you do the experiment. The absorbance values are coming from the instrument. Okay. Now the next row after that, now the blank column has been, well, blocked out because the blank does not go to equilibrium. So once we hit the part where we're looking at equilibrium, we no longer care about the blank because again, it's not allowed to go to equilibrium. It doesn't react. We didn't add an important chemical. Okay. So for the test tubes 1 through 5, which I guess are not test tubes, but the reactions 1 through 5, are for the equilibrium of the product, well, that absorbance is of the product. So you know the absorbance. You know the extinction coefficient from part A. The path length for spectrophotometry at St. Charles Community College is going to be 1.00 centimeters. C is equal to the Fe NCS2 plus at equilibrium value. So you're using Beer's law to solve for that. You'll have to do that for each of the reactions. They all have their own absorbance, so do the math necessary. The extinction coefficient and the path length don't change, but the absorbance does. So at this point, I didn't really give myself enough space. We will have 3 calculated numbers: the initial iron, the initial thiocyanate, and the equilibrium product. So that equilibrium product, it's like it could go in there, but I don't know the equilibrium of these two. So one more slide. Equilibrium, Fe NCS2 plus. We have 2 initial values and 1 equilibrium value, and our job is to solve for the other 2 equilibrium values. Hopefully this is ringing some bells on things that have happened in lecture. So you're going to be doing an ice table for each of the 5 reactions that you did in part B. That's how you're going to solve for the equilibrium iron and the equilibrium thiocyanate. So there's no way around an ice table. Okay, you have to do an ice table. So let's go with, pretend like this is one of the reactions. If my initial iron number that I already calculated was 0.000100, and my initial thiocyanate was 0.000200, okay, your product initial value is 0 because you didn't pour, like when you did your pipetting, you didn't put any of that chemical in there. But you will know the equilibrium number coming from Beer's law. Okay, so we can look at the change row. In the change row, one side of the arrow is positive, one side is negative. This one's going to be positive, this one's going to be negative, because 0 has to increase to become 7.90 times 10 to the negative 4th. There's a 1 to 1 to 1 mole ratio. So that tells me 0 plus x equals 7.90 times 10 to the negative 4th, which lets me solve for the other values. So I have to do the subtraction. And this one would be 0.000. Wait, no. Yeah, no, that's good. 2.210. Sorry, my math is being screwy. Okay. So I'm just, oops. I substituted this value in for x. Okay, and when I did that, I get 0.00121. So that's how you're going to get your equilibrium values. Okay, for iron and thiocyanate. So you're going to do an ice table, and you're going to solve for what the E row is, and then you're going to write those in that block. And then the last thing you have to do is write Kc. So you're going to have to calculate that for each reaction. So you're just going to take the equilibrium constant expression, which we've written like, I don't know, I feel like a bunch of times now, but I think that's just because my hand's getting tired. I'm just plugging in the equilibrium numbers in their appropriate spots. And when you do this, your equilibrium constant, like for my example, it was 311. That's in the range of what it could be. Everyone's could be slightly different for your equilibrium constant, but probably in the hundreds. Probably 200 to like 800 would be my guess on what they are. It depends on what the temperature in the room was. It depends on which instrument you're using, etc., etc. Oh, and one thing I wanted to mention that I didn't, your extinction coefficient back in part A, the number that we are going to use then to solve for the equilibrium concentration of the product, it's going to be a super big number. Your extinction coefficient is like, it's large. Okay. So, it kind of depends what on your instrument and that kind of stuff, but it's going to be a big number. So the last lab, it was like 200. It's going to be bigger than that. For some people, it's up to like 2,000. So don't be surprised if it's a really big value. Now, I left space, so then you have to calculate the average equilibrium constant. So after you've done the equilibrium constant calculation, so, you know, this calculation for all 5 of the reactions in part B, then you're going to average the equilibrium constant, and then you're going to standard deviation it. Now, one thing I didn't mention, but I want to now, right above the part B data table, it says, use 3 significant figures for the equilibrium concentrations and Kc values in the below table. So I'm telling you that as you do the math to solve for things, I'm telling you up front, use 3 sig figs. Okay, so use 3 sig figs as you do this table. Since there's so much subtraction that's going on, like, you know, here and here, it's easy for things to, like, sig figs get complicated when we're combining addition, subtraction, multiplication, division, and since you're doing ice tables and there's so many of these, I'm just going with 3 sig figs for everything. So since I'm giving you that, I'm not going to be super kind if you use the wrong number of sig figs because I'm literally telling you how many to use. Okay, 3 sig figs for everything. The blank space that I give on the next page and then on the page after that, the reason why there's this empty space, well, you're going to be doing 5 ice tables. You have to show me one of them. I would strongly suggest go ahead and do the other 4 because you have to anyway. The numbers are not going to be the same for your 5 ice tables. You can't just repeat the same numbers. You're not going to have the same values for all of the reactions. So again, I would just do them. Post-lab questions. Number 2 and number 3, you cannot do until you've gotten done with your data calculations. You have to use your equilibrium constant, your average Kc value, whatever the average one ends up being, to do your problem for number 2. And I'm just giving you a mega hint. Number 2, you're going to have to do the quadratic formula. There's no way around it because your equilibrium constant is not going to be small enough for you to do the shortcut. And so you're going to end up having to do the quadratic formula. So what you're doing in number 2 and number 3 is trying to kind of prove that it was okay for us in part A to assume that part A didn't go to equilibrium. We're trying to prove, is that really true? So we're treating it like it's going to equilibrium and then seeing what our numbers tell us. So what we said in part A, oops, where is my part A stuff? Nope, that was part B. Part A. Here, there we go. What we said in part A was that the SCN minus initial is equal to the FeNCS2 plus equilibrium. That's what we said in part A. So what you're testing in post-lab question 2 and 3 is that true? Okay, so that's what you're calculating in number 2 and answering about in number 3. Now numbers 4 and 5, you are not using the quadratic formula. So if you ended up using the quadratic formula for any question other than number 2, you're doing it wrong. But 4 and 5 have nothing to do with this specific reaction. They're just other equilibrium problems, so you can do those before you've done all your calculations. You will have 1 Excel graph for part A, 0 Excel graphs for part B, and that Excel graph is part of the lab report.